So in this module, what I want to do is I would just want to elaborate more on the square wave example that we saw previously. So once again, consider this square wave of a period t. We've determined in the previous example that the Fourier series coefficient corresponding to this square wave are given by this, right? So the a naught is 2t1 by t, whereas all of the other a k's for k is not equal to 0 are given by these expressions. So what Fourier series analysis or Fourier series expansion really states, therefore, is that if I plug in these a's that I've determined here into this expression, what would end up, I would get up ending is x of t, which is actually a square wave. And then that may sound a bit counterintuitive to some, because what you're really doing is you're adding up sinusoids, which are continuous signals, and you're adding them up. And this expression is telling you that when you add them up, you're going to get something which is a nice discontinuous square wave. Now, in order to verify this, I'll urge you to try to implement this in Matlab. So can we really get a square wave by adding scale complex exponentials as indicated by equation 2? And in this exercise, you'll try to use Matlab to verify this. And of course, in Matlab, you will not be able to implement this infinite sum. Rather, you will just implement an approximation. So let that approximation be x sub n of t. That's an approximation where you're just adding up the harmonics from k equals minus n to plus n. So we say we're adding up n harmonics. And for a particular omega naught, for a particular t1 and a particular n, you just try to plot it out in Matlab. And what you'll observe is that as you keep on increasing n, you will get something which is closer and closer to a square wave. Now, this is something that I've done already. I'm just going to show you results. Okay. So here is Matlab depiction of the original square wave. So this is a square wave similar to the one that you saw earlier, except that this square wave has a period of 0.02 seconds and t1 of 0.005 seconds. Corresponding to this, these circles that you see are actually the Fourier series coefficients. So this is A naught, this is A1, this is A2, this is A3, A4, and so on and so forth. This is A minus 1, A minus 2, and so on and so forth. And you can see what they are. They reside on an envelope of this nice, this pulse, which is actually called the sync pulse. So we're going to see this sync pulse a little while later in the course. And given these coefficients, what I want to show you next is how when they add up, you're going to get something which is close to a square wave. Let's look at that. So this is the approximation x sub n, where for this figure that you see here, n equals 1. So you're just adding up the first harmonic, and what you get is a sinusoid. When n equals 2, there are two sinusoids being added up, but both of them are scaled appropriately by the coefficients that we've derived in the notes. And you start to observe that this is closer to a square wave as you increase the number of harmonics. For example, number of harmonics equals 6, n equals 6. You get closer and closer to a square wave. N equals 16 is even closer, and you can verify that as you keep on increasing n, you get closer and closer. However, one of the things that you can observe are these peaks here. You're never going to be able to get rid of this. And this is something called the Gibbs phenomena. I'm not going to go into a lot of details about this. You can read this in your textbook as well. But the bottom line is that as you keep on increasing n, you get closer and closer to a square wave. So indeed, you can verify that the Fourier series decomposition is really indeed true for this square wave, the way we've derived it in the previous session.